So we mentioned ecosystem-based management a few times. So let's just look at in a schematic what it means. Okay, so when we do single species or sector-based ecosystem-based management, you are trying to either manage a particular fish that you are trying to catch, or you're trying to work around some human activity like offshore drilling, oil platform, and so on and so forth. When you do multiple species or sectors under ecosystem-based management, then you are trying to see how the local interdependence of the species works, or you are looking at the fisheries of a single species versus other human activities. Okay, but if you do ecosystem-based management of the entire system, then you are going to worry about climate, multiple species, fishing pressure. Okay, this is an external pressure because it's not like agriculture that you put in seeds and then you're harvesting fish. You're just going and exploiting wild fish that have to manage on their own to breed and reproduce, right? So other human activities, marine resources, you can think of it, coastal habitats, maybe offshore wind energy or wave energy, people's use of coral sites for diving, beaches, whatever else, and protect megafauna like whales. And this one I have no idea what it is, but it's something. So essentially you have to manage the whole system, right? What are the things that can get in the way? So this is the map of the marine heat waves in the last 2 decades or so, where the temperatures at each location here exceeds some threshold. So if you have over a year certain temperature range, when the temperatures exceed 95th percentile of the maximum temperature you get, so 95th percentile is the warmest temperatures you get at each location, then you can look at how long those exceedances happen, how often the temperatures go into the 95th percentile. So you look at many years, find the warmest temperatures and the lowest temperatures, and you look at when the maximum temperatures happen in the top 95% or coldest temperatures, depends on how you look at it. And peak temperature anomalies. Okay, look at these anomalies. These are all warm anomalies, so we are looking at heat waves. This whole region has had anomalies as large as 5, 6, 7, 8, 9 degrees. So if you are any marine species that is used to living in a region and you get a number of days of heat waves, sometimes greater than 100 days of warm temperatures, warmer than normal by 5 degrees. That's really hot, right? And this is the cumulative intensity in terms of degree days. Okay, so that's another measure. Okay, so this is what is happening with global warming. So when you do ecosystem-based management, you will have to worry about the climate impacts as well on not only reproduction but also the entire food web. So here is an example. We have El Nino and La Nina. So 97 November was the peak of the 97-98 El Nino. Remember, El Nino comes during Christmas, so December, January, February. So by November it was already pretty warm. This is shown in terms of sea level. So sea level was much higher than normal. Remember, upwelling cold water means low sea level. El Nino warming and reduced upwelling means high sea level, right? So high sea level of more than 14 centimeters above normal. And this is February 99 when there was a strong La Nina. So the sea levels were below normal by almost 16 centimeters. Very strong upwelling, very cold temperatures, and you can see that here. So this is the index of temperature anomaly in the middle of the Pacific, tropical Pacific here. So it's showing when it's well, this is actually showing the southern oscillation, which is the pressure difference between Darwin and Tahiti. It's the same as El Nino, but opposite in so when southern oscillation is negative, there is a El Nino. When it's positive, there is a La Nina, and so on. So blue colors here are El Ninos, and red colors here are La Ninas, I hope. 97, 98, yeah. So I hope I'm right. Maybe I have reversed it. 82, 83, 90. Yeah, so I'm sorry. So red colors are El Ninos and blue colors are La Ninas because of this southern oscillation. Temperature would be warm, sea level would be, SOI would be negative. But anyway, looking at this, you are going to affect the temperature and nutrient supply because you are affecting upwelling. So you would affect phytoplankton and zooplankton. You would affect the next member in the food chain like anchovies, which are eaten by hake, which is eaten by fur seal. Okay, so food availability is going to be affected by this. Okay, so this is not fun. This is another example on land, how the effect. So basically that means when you have, whether it's natural variability or global warming, it doesn't just affect one species, it affects its entire ecosystem from the food supply to its reproductive times. So the seasonality can change, so the reproductive ability can change, fertility rates can change, and so on and so forth. So ecosystem based management has to account for all of that. Okay, remember that it's not a very simple issue, it's fairly complicated.